Section 3.2, now that we've gotten the basics out of the way, we're going to look at conditional probability and the multiplication rule. So the big part of this first video will be over conditional probability. So let's define that. What is conditional probability? Well, simply put, it is the probability of an event occurring given that another event has already occurred. So one that's actually happening right outside my window is I'm hearing thunder. So maybe, just to put this into a conditional probability, it's like, you wake up in the morning, what's the chance it's going to rain today? Oh, I don't know, 20%. And then you start hearing thunder outside your window. Well, your 20% just went up because now you've heard thunder. So that means rain's pretty close. It's not guaranteed that you're going to get rain, but it's close enough that you're hearing the thunder from it. So it may not be 20% in your mind anymore. You may be thinking it's more of like 80%. But anyways, so conditional probability is the probability of an event occurring given that another event has already occurred. So when we see this, it often looks like probability of B, and then there's some line, and then an A. The way we read that is the probability of B given A occurred. That's how you would read that. And we do have a formula for that. We can say that the probability of B given A is equal to the probability that both A and B occur divided by the probability of A. Like, well, how did you know to put A on the bottom? The reason we put A on the bottom is we know that A's already occurred. So I want to find the chance that they both occur. You're like, huh, what? This still doesn't make sense. Let's draw a picture. Let's draw a picture. I like pictures, especially when they have pretty colors. Okay, so there's our sample space, and I'm going to have, this is going to be event A, and then let's do event B. So if this is A, and then the green circle is B, the probability of B given A is, I'm going to need to, let me change this to switch background. There we go. That way we can see what's going on here, because I'm going to have to use a highlighter. Okay, probability of B given A. I already know that A has occurred. So I'm going to kind of shade in all of A right here. I know A occurred. So now my sample space, if you will, has shrunk. Instead of being S, the whole rectangle, now it's just A. The probability that B given A occurs is this intersection right here. That's why it says A and B. So probability of A and B, that's the green area. Probability of A is our blue area. That's a visual of what's going on. So it reduces the sample space to only what's given, being that A occurred. So let's kind of put this in terms of cards, like drawing from a deck of cards. Now, for those that don't know what a standard deck of cards is, or what's all in a standard deck of cards, I'm going to put an image out there. That way you can clearly tell. So, copy image. Paste. Okay, so this is our standard deck of cards. So, go here. Standard. So we have 52 cards total. We can see the black ones. The black is clubs and spades, red's hearts and diamonds. But that's our standard deck. Now, where's my text at? There it is. Come down here, buddy. Okay, let's look at example number 1. This one is going to be a word problem. Cards are selected in sequence from a standard deck of 52 playing cards. Find the probability the second card is a queen, given the first card is a king. Assume the king is not placed. Okay, so we know that we pulled a king out of this deck. So the way I like to think of this, the king is gone. So one king gone. Which means how many cards remain? 51 cards remain. So we pull the king out, 51 cards are going to remain. How many queens remain? Well, if the king is gone, there's going to be 4 queens. So the probability that we get a queen, given we have a king, would be the 4 queens that remain out of the 51 remaining cards. So again, one king went away. So now that 52 card deck is down to a 51 card deck. But all 4 queens are still there. So that's why I got 4 out of 51. That's conditional probability. That's about as simple as I can put it for conditional probability. Okay. Let's look at another example. This next one is a bit more typical of conditional probability, in the sense that we use a table. Example number 2. It's also a word problem. Okay, the table at the right shows the results of a survey in which 2,276 social media users were asked whether they have ever been offended by something they saw on social media. The probability that a user is male, find the probability that a user is male given that the user was offended by something on social media. This problem always seems to crack me up, not because of the math behind it, but just because in the day and age we live in, so many people want to let you know that they're offended by what's on social media. Like, okay, you don't agree with it. Move on. Somebody agreed with it, so they posted it. You don't agree with it? Move on. You don't have to let the whole world know that you don't agree with it. And then belittle the person that posted it. Anyways, I digress. So, let's think of our formula. What does our formula say? Our formula says the probability of event B given A occurring is the probability that A and B occurs over the probability of A. A is always what is given. So where do we say given the user was offended? Okay, so that means that A is going to be offended. So event B has to be that they are male. Okay, so what does this look like in action? Well, I want the probability of offended. No, I don't. What did I say B was? I said B was male. I want the probability of male given offended. I'm just going to say off instead of offended. Okay, so I need the probability of male and offended over the probability of offended. Now, I know I'm listing probabilities here. These don't have to be probabilities. They can be counts. So how many were male and offended? Well, I come to my chart. Male, and then yes, they were offended. So that's going to be 532. 532 were male and offended. Now I have to look at how many were offended. Well, both of these values under the yes column were the ones that were offended. 619 plus 532. There we go. Now we just calculate. So that's going to be 532 over, if I add those together, I get 1,151. Which as a decimal, this comes to 0.462. Okay, not bad. No, the problem doesn't have a part B. Let's add one. Let's add a part B to this. So, I'm going to actually put that here. Let's add a part B. Find the probability that a user was offended given they were male. All right, well, that's the same thing, isn't it? Let's think about it. Let's write in math language what this is asking. This is asking the probability of offended given male. Okay, so if I think of what's going on here, this is the probability of offended and male over the probability of male. Oh, wait a minute. They have different denominators here. Offended and male, so sure, the numerators are the same, 532, but the denominators are different. Now I'm dealing with males. So 532 plus 576. Oh, different denominators. So we're going to have 532 over, and then let me, these 532 plus 576. That's going to be 1108. So now we do indeed have a different denominator. I divide these are roughly 0.480. That's different. So what's the takeaway then? Why did I have us add this part B? It's because I want you to notice that the probability of male given offended is not equal to, I guess that's a little bit, is not equal to the probability of offended given male. So don't get caught up and think, oh, these are the same thing. No, they're not. They are different values. The probability that someone's offended given they were male is 0.48. The probability that someone's a male given they were offended was 0.462. So different probabilities. For those of y'all that want to be devil's advocate and say, it's basically the same thing, they're close. Remember, close only counts in horseshoes and hand grenades. They're not close. Okay, so that's it for our intro to conditional probability. Stay tuned when we talk about independent events.